Thank you. Okay, so let's start with the talk. So hello everyone. This talk is titled as "Unveiling the Private Federated Learning and Model Compression for Secure AI at the Edge." Before starting, I'll set some context about why why we are concerned about this privacy and how privacy comes into the play when we are going into this AI world. So imagine imagine you are training a world class AI model on millions of smartphones. So all the smartphones, edge devices that everyone has, right? All all the models are being trained on these edge devices without data leaving your phones. So this isn't science fiction, and it's happening real time. Many companies have been adopting to this new technology, and it's a I would say a revolutionary approach in the AI development, and that will keep your data private while you are training your models. So this is a privacy versus power struggle. And with this introduction, I'll like to introduce myself as well. I'm Gautam. I'm currently a final year undergrad student at BITS Pilani. I am also interning at Microsoft Research. My Mainly, my research is focused on federated learning, distributed systems, and currently I've been into LLMs about studying about reasoning and prompt optimization. So, yes. So let's start with an example. So this is a real life example, and this is a snippet that I have taken from the website of Google Keyboard. So everyone, most of the Android users, I would say, would be using the Gboard that we have. And I would like to quote this excerpt that is mentioned on their website. So they mention a technology called Dash. I have blanked the space because we in this talk will lead to what this Dash or what this X is going to be. So a technology called Dash helps Gboard learn new words and phrases. So Dash doesn't send the text you speak or type to Google, but it will send whatever it learns to Google, where it will combine with learnings from other users. So this is an example that is mentioned on Google Keyboard. And just to quantify the use of this technology, after using this technology, the increase in accuracy was seen around 24 to 25%, and the useful prediction strip or the number of clicks, right? This was increased to around 10%, and all these quantified numbers are mentioned basically on one of the most important papers in this technology by the Google Keyboard prediction team. So this is how impactful in terms of numbers is while we use this technology that will get to that we blanked out in the previous example. Now let's go to the second example. So first one was Google and second one was Apple. I would like to show the highlighted box there, and which mentions that Apple relies primarily on a technique called Dash. The head of privacy mentioned this in one of the MIT review blogs, where they say that this was introduced by Google in 2017, and it allows Apple to train different copies of a speaker recognition model. So these two examples are just to show that how companies have been using this technology for this new data privacy issues while keeping the accuracy of the models constant, or while improving the model accuracy of these models. So let's start with a context or background of this privacy versus power struggle in ML. Currently, so let's start with this data privacy challenges, and I have mainly subgrouped data privacy into five main headers that are data breaches, lack of user control, compliance and legal issues, scalability issues, and ethical concerns. So as we know, central ML algorithms have transformed the data management and analysis industry, because these centralized ML algorithms need data for increasing their accuracy and for better prediction or for automating tasks or whatever task they are doing. But due to the extensive use of the personal data by these ML models, what these privacy concerns arises, and some of these, let's get deep into these privacy concerns. So first is the data breaches. So data breaches is basically if you have a centralized data storage and all the data of all the users is at a single point. So this creates a single point of failure, and all the hackers or all the type of cyber attacks would be this centralized database would be a very lucrative thing for them, because it will be an attractive target and they would target the centralized database. Hence, this is a potential privacy concern, data privacy concern that is coming up, that is the whole industry is facing. Second is the lack of user control. So since all of this data is being transferred or is being communicated to these organizations, so you don't have any control about what type of data is going to these organizations. So as a user, it's very concerning about what type of data these organizations are having about yourself. And this is a second privacy challenge, data privacy challenge, that I would like to mention. The third is the compliance and legal issues. So compliance and legal issues, so as you know, in Europe and in different parts of the world, so we have GDPR or the CCPA compliance, various regulations have been introduced, and a lot of legal battles, like behind the doors, a lot of legal battles have been happening between these top MNCs or the organizations versus the state, and where they are not complying or where they are losing these challenges or these legal battles. So this is a very main concern for these organizations. So how do they proceed? So the fourth one was scalability issues. If data is at a single storage, if we have a single storage data and all the data is at a single point, how do we scale? So we should have some shredded management or some way that data is being is at different places, and we don't have a single point of failure, and we can easily manage large scale data. So this is the scalability issue of the data privacy challenge. And the fifth one is ethical concerns. Obviously, ethical concerns often revolve with sensitive personal information, and which mainly, I would say, overlaps with lack of user control about how these ethical concerns are managed by these organizations. So this is one of the example this is a very famous scandal that happened of the Facebook owner settled the class action suit with Cambridge Analytica, and I'm sure like many of you would know about this scandal, and this is one of the most famous one, and these kind of data breaches are happening on a regular basis, and this is a main concern for every other organization. So let's move on to this privacy versus power struggle, right? This is one of the images I took from the Netflix blog, where they have this recommendation system. As you can see, there is this image is important because I wanted to show to increase the efficiency of these ML models, or to increase the accuracy. They have this database layer or the data layer where the data is being inputted to, is an input to these ML models. So large volumes of data is needed to get larger accuracy, but more data leads to a user's risk to users' privacy. And this trade-off between models accuracy versus privacy, it is the heart of the privacy versus power struggle in ML. And it's delicate balance, because you have to get better results but keeping data private. So this is a trade-off or balance that everyone needs to keep in mind. And and users should be aware of what data is being kept by the organizations, or what data is being used for increasing these ML models. This is just a representation about how fairness, privacy, and accuracy come into play with the deep learning model or any ML model that we have. So what are the possible solutions? If I would say that what could be done, so everyone who have some experience in ML would say, okay, we need data to increase the accuracy, but what are the possible solutions? What you can think of? So I would just say, think of something about how we can go about this thing, how we can increase how we can tackle this challenge. So I'm a diehard Silicon Valley fans, and I'm sure like people would be there who would be Silicon Valley fans. So this is an example from season 4 where for those who don't know, who haven't watched Silicon Valley, it's a TV show, and I'll explain what happened here. So they lost all their users' data, and then this data was distributed among different appliances. This is an example where all the data was distributed on different smart fridges. And so if data can be distributed among these different devices, so what's the possible solution? Can we do something with this? Can we use this possible solution to tackle this data privacy challenge? So the answer is yes, and this is a revolutionary technology called federated learning. I would quote all the lines that I have mentioned because it's from one of the most important papers, research papers that have been published, or the initial papers. So federated learning is a decentralized approach to train ML models. Instead of aggregating data at a central server, FL enables models to be trained locally at user devices, and only the model updates are sent to the central server for aggregation, such that the raw data never leaves the device. So it's pretty simple about how the definition goes. Like, there's a central server which would maintain the orchestration of all the models of all the clients, but data is not leaving these clients. Only the model weights have been sent to the central server. So how FL addresses this power versus privacy tension? So data stays local. First, all the data is local to the client's individual device. Second, enhanced privacy. Obviously, if the data is not being sent, we have an enhanced privacy, and all the data is being private to these users. And third, it maintains model performance. So let's take example, there are two people, A and B, and A is getting to learn about B's user preferences without actually seeing their data, and only sending the weights. And so the accuracy obviously increases, or if not increases, if we maintain the same accuracy, that's also a big plus advantage, because we are keeping the data private. So this is what FL does. And so the next question is, okay, if FL is useful in orchestrating all these if FL is useful in orchestrating all these, this system where data is being kept private and only a central server is handling all the model weights. So how does a mobile phone, which is probably 4 or 8 GB, or like depends on the configuration, how does large ML models are trained on these smartphones or on these edge devices? So one of the edge devices is, I'm just talking about smartphones. It can be smart fridges. It can be different devices such as Raspberry Pi if we go on to edge devices. So how do we ensure that these billions of parameters in the models are being trained on the user's device? So we introduce second thing after federated learning is the model compression. So model compression is basically using different techniques to compress model. So while compressed model means that we have a shorter model which does not take a lot of space but gives the same accuracy. So this is the second thing. After federated learning, we have to apply model compression so that we can achieve the real-time simulation, or we can achieve to what or all other organizations are doing. So next section would be, let's get deep dive into FL, how federated learning works. So federated learning involves basically 3 steps. So first step is the model initialization. So for any particular problem, say let's say classification problem or any problem, the first step would be model initialization, where you would get to know about what model do you want to define. So first, if you have defined a model, second would be so this model would be then sent to these different clients or different nodes or different users that you have in your whole system. This model initialization is sent to these devices. So all these devices have this model sent by the central server. This is the first step. Second step would be to locally train the model on the data that a particular node has. Let's take an example. We have 3 devices. So first one is smartphone, second one is some smartphone, and third one is laptop. So every device would have some data personalized to it. They will train that ML model on the data that they have, and this second step would also involve, after training, they will send this model weights. If in ML models, we usually, it is represented by weights. So we send these weights to the central server. So this is the second step. Once these weights have been, we have all these weights from each and every client at the central server, we aggregate all the weights and create a updated model, and then again send this updated model to all these devices. So using this system, a smartphone is able to learn from the C, that is laptop, while keeping their data private to their original, to their own system. So this is how good FL is while making the system. And so this is just a life cycle of FL trained model about how FL trained model in a real life looks like. So first, there's a problem identification. So if you want to make a same system. So what do? First, you have to identify the problem that you want to solve. Maybe it's a classification problem, maybe it's a generative problem. So it depends on what type of problem you have. Then you do this client instrumentation, where you select the clients that you want to use this process with. So you will select basically the different users based on some defined setup, defined parameters. So you have this client instrumentation. Third is the simulation of prototyping, just to sure, as an engineer, what you will do, just to test if this is working fine or not. This you simulate. Fourth is this actual federated model training, where training happens. And then fifth is evaluation. So evaluation means that how good the central model, the FL model is being, how good the FL model is. And then also selecting the best clients, or the clients who are actually contributing to the system. And then sixth would be the deployment on various devices. So this is how this is a life cycle of how engineer thinks of when FL model they have to deploy. So yes, let's move on to the real-time FL simulation, where we can actually check how FL works. Yep. So before this, before we move on to the simulation or the code, I'd like to mention about this Python library that we'll be using, which is MPI, that is message passing interface. So MPI is one of the go-to libraries for parallel computing or distributed computing. I'll just brief you about how MPI works so that it's easy to understand the code. So basics of MPI uses 4 things. First is the process. So each process, or whenever we are training the model, each setup is a process, is an independent execution unit. And then we have a communicator who orchestrates all these processes. Ranks are basically, we just, to identify each client, we give rank. So it's consider it as a serial number, or a node ID, or a user ID. And then we have message, that is in our case, a message is basically model weights that we would be sending to the central server. So how MPI is used in FL? So in a client server model, node 0 is as the server, and all the other nodes are nodes that are participating in the FL system. And all this is being happening while all the nodes are parallelly run through. And this is efficient in communication, scalable, and the aggregation of model weights is easier. So yes, let's visualize MPI in action while looking at the code. So the code is relatively simple, I would say. So this is general stuff about how an ML, how you will train an ML model, and this is some data pre-processing that is happening. We are using an MNIST dataset, which is one of the famous datasets. It contains digits. With respect to MPI setup, which is our main focus here and not the ML model basically. So MPI setup, COM is one of the communicators. So treat it as a in a Venn diagram, right? Treat it as a total big circle in which independent processes are being executed. Rank and size would give basically the rank and the type of message that that the node will be sending. And this is some data pre-processing stuff happening. And we are obviously not concerned about how ML model looks or what type of parameters that we are sending. So yeah, just to show about the difference between centralized versus the centralized traditional training process versus the FL training training process. So what I'm doing if the rank is 0. So as I mentioned, rank 0 leads to a server. So for server, I'm just doing a centralized learning. So all the data is on the central server just to check what's the difference between if we deploy FL training model or if we deploy a centralized machine model. So this would give some accuracy, or this would give some graph. And now we move on to this FL federated learning system. We have defined some hyperparameters like number of rounds. So for each round, what we do is, so the local model is for a particular node. This local model is there, and this local model is then trained on the data that the particular node has. After this node, we'll get the weights of the particular model, and then at rank equals to 0. So then at server, what we are doing is we are appending all the local weights that we have, and then we are averaging all the weights. So there are different algorithms. So here we are using Fed average algorithm, which just averages all the weights that we get from different nodes. So we get average all the weights. We set the model with these averaged weights, and then we send back again. So here we send broadcast all these weights, or in terms of model. So we send this model to all the broadcast to all the nodes. So this is how FL system would look like, where we have a central node which is aggregating all the weights. So just to show, I'm not running this code. I have run the code, and this is the final result that we have. You can see at the 0th round, the accuracy is very low, obviously because the user doesn't have any data, because the server doesn't have any data, or there's no update in the weights. But as different nodes participate, the accuracy improves, and we are getting close to same as centralized learning. And in terms of when we deploy it in different tasks, right? It many times, like almost most of the times, it outperforms centralized learning, because you are able to learn from different users, their preferences, while keeping the data private. So hence, this is a very important graph that shows the difference between FL learning and centralized learning, and on MNIST dataset. Yep. Back to slides. So next step would be, after deploying these models in a FL system, about model compression. So model compression is a very, I would say, it's being researched or done very from late 2000s, and like from a very back. And we need model compression because to deploy these models on these edge devices, we have limited computational challenge. We have limited computational power, and then we have restricted memory, and there are energy constraints. So obviously, we need to compress these models to make these models run on these edge devices. So what are these techniques? So one of the techniques is quantization. Quantization is basically where we by default, all these model weights are stored in 32-bit floats, while now what we do after quantization is we convert it to an 8-bit integer. So 22-bit floats are converted to 8-bit integers, and now the thing is 32-bit, so we are saving 4x amount of memory here, while 4x amount of memory, while keeping the accuracy same or slightly slow, because it's a trade-off between the accuracy and the space it will take. So sometimes this is when deployed, this gives better accuracy because there would be some cases where 32-bit floats won't work and 8-bit integers are working perfectly for the model. So for quantization, there are basically two techniques, I would say. First is post-training quantization. This means that you have trained the model, you have the global weights, and what you do is just change these 32-bit float weights to 8-bit integers. So this is a post-training quantization. And the second one is quantization-aware training, which is done while, so quantization is done while you are training the model. This is very sophisticated and important, and most of the BERT models, so QBERT, so BERT models are the used in NLP, and this QBERT called quantized BERT models, and these have been used, and NVIDIA specifically, if I would like to mention this organization, they have been working a lot on the model compression things, because their main aim is to deploy this model on their chips, and doing this requires some quantization and different model compression techniques. The second one is pruning. Pruning is, so consider this neural network where you have different, where from different neurons you have different edges. But after pruning, what you can do is you can check if you can remove some less important weights. So there's a way where probably you can check that these like the neurons that are connected by these edges are not needed. So you remove these edges from before pruning, and then you get a pruned model, so which has a fewer edges than what we had previously. So a typical process looks like we have a model, we prune that model, basically remove the edges, less important edges. We have a pruned model. After the pruned model, we quantize, basically converting that 32-bit float numbers to 8-bit integers. And then we have the final model, which is being deployed and which is being used by everyone, by the users, at the users or at the edge devices that we are mentioning. So yes, for conclusion, FL has various applications. So first one is healthcare, where you are keeping the data or the data of patients and doctors private, and this is actually being deployed in Europe, and a lot of research is being done in Europe, particularly about healthcare and how FL is used in that sector. Second is edge IoT, which is edge devices. For example, the smart watches that you are using, how heartbeat is monitored, and different things that is being monitored using this smart the smart watches. And third is finance sector. Obviously, in the finance sector, all the data needs to be private. One of the use cases I have in mind is the credit fault risk. If you have to assess, but if you want a bigger picture, if you want a larger data, you have to keep that private. But if you want to build an ML model, so JPMC is one of the organizations that is working on. And yep, just to finish it, so FL, this is one of the comics that is from the Google's FL website, and what they are mentioning, probably, yeah, you can see. They are mentioning, I'm back from the conference and I know we can win back our users. So I would also like that if everyone probably mention this when they go to their own organization or project that they have come from conference and they have learned about FL. And yeah, just to end, this is a snapshot of how FL is being used for Google Keyboard. You can see on 18th and 19th September, Federated computation check-in is the device attempted to participate in a federated computation. And it's just to show that it's being real-time, and FL is being used for Google Keyboard. And you can also check the logs on your smartphones. Yes, thank you so much. Yeah, if you have any questions, yeah, glad to take.
Take the questions offline?
I can take the questions offline.
Thank you so much, Gautam, for the talk, and to just appreciate the amazing thing that you've done with us today. It's a small goodie for you. All right. On that note, folks, we will start our next talk at 11:40 in the next 3 minutes.